This is a production of Cornell University.
So welcome everybody. We have a really exciting panel discussion today on the topic of GHG emissions from agriculture as it pertains also to carbon sequestration. Try to bound this, this topic a little bit by the consideration of what's really possible. And essentially looking back in retrospective mode to see sort of what's changed over the last decade, what we've learned, and having some critical thoughts about how we move forward. So, you know, we have a really fantastic panel here today. Cornell has the advantage of having global expertise in global carbon cycling, atmospheric dynamics, all the way down to soil scientists who work both at the fundamental level, but also on agronomic management options. And we have the good fortune of having four of our really global leaders in this area join us today for the panel. We have Natalie Mahowald, who's the Irving Porter Church Professor in Earth and Atmospheric Sciences. We have Peter Woodbury, who is a Senior Research Associate in Soil and Crop Sciences within SIPS. We have Dominic Woolf, who's also a Senior Research Associate in Soil and Crop Sciences in SIPS. And we have Johannes Lehmann, who's the Liberty Hyde Bailey Professor also in Soil and Crop Sciences. So we have a really fantastic panel today. I should say that this is really timely to have this. You know, you can't go 30 seconds if you're paying attention to the scientific media, mass media on these things without a mention of regenerative agriculture or the potential role for agriculture to reduce net GHG emissions. But there's a lot of a contention around how we get there. And the panel today is meant to point us in that direction. The way it will go is that we're gonna have 4 lightning talks in the order that I introduced the speakers. Then we're gonna pivot to a panel discussion that will take us to about 1:20. And then the final 10 minutes or so will be open questions from the audience. So please keep those in your pocket, type them in the chat if you have to go, and we'll pivot to them at the end of the session today. So with no further ado, I think that Dominic, you're in the lead on transitioning between slides, and everyone else, please make sure that your mics are muted, and away we go. Thank you to the panel for pulling this together.
Well, thank you, Andrew, for moderating. I think I'm up next here since my slide is on here. And what I want to emphasize, you know, I'm not a soil scientist. What I want to emphasize is really what do we need to do to meet the low carbon targets. So I'm Natalie Mahowald. I'm not going to talk about my own personal work with Earth System Science or climate models. I'm really just going to present the IPCC, Intergovernmental Panel on Climate Change, results here and the context for soil sequestration. What do we need to do to meet the low carbon targets? One really important point that I find that a lot of people don't really understand is climate change has really long timescales, and that's really what we're trying to get after. So in this slide, this is a classic climate change kind of slide where we start, you know, the x-axis is 1850 out to 2100 here in the middle, or 2300 to the right. So this is the kind of view I have of the world, these really long time scales. On the y-axis, that's the temperature change. And you can see, you know, up to 2005 for this particular plot from the last IPCC assessment report. You know, that's the historical time series. And right now we're at a crossroads where we can go on the red trajectory, which would be business as usual, which, you know, 2100 might be 4 degrees C, 2300, 8 degrees or more C, versus if we act right now and we completely change our economy and start sequestering carbon as much as possible, that's this lowest blue line. So really, we're acting now to have an impact at 2100 or later. So it's a really difficult problem for politicians to get their head around, but also for humans to get their head around. But it's really important to understand climate change has a really long time scale. Next slide. The other point to make is that it is the cumulative CO2 emissions, which is on the x-axis here, that linearly relates to the temperature anomaly relative to pre-industrial. And there's a little bit of noise up and down in this. You can see, from short-lived gases like methane or aerosols, or exactly the trajectory. But almost all of this is CO2 emissions are dominating. Now, nitrous oxide emissions also have a really long lifetime, so they could also be included here, but are much, much smaller in magnitude. But the reason we only think about the cumulative CO2 is because of the really long lifetime of CO2, which is thousands of years, and how much CO2 we emit, okay? And the really important thing to understand is that until our net anthropogenic CO2 emissions go to zero, we will continue to have climate change. Under the Paris Agreement, we're going for 3 or 3.5 degrees. Yeah. Who's going to cause most of our climate change? It's developing countries if they use our pathway. I mean, that's how we got here to our wealth and our lifestyle is by emitting a lot of CO2. And developing countries, of course, want to have our lifestyle. Why wouldn't they? And they want to have our long lifetimes with really good healthcare. Well, okay, maybe we don't have that, but we have better healthcare. And an incredible thing is happening right now, or was before COVID, is we might actually be able to eradicate extreme poverty by 2030, and we have the Sustainable Development Goals. And you can see this in this slide, again, going from 1820 to 2015, that the number of people in extreme poverty has actually gone down over the last 30 years. So this is incredible. This would be great if this happened. But the bad part is right now they're following our development pathway, which is the cheap way to do it, which has emitted a lot of CO2. So this is the real dilemma. It's climate change versus development for a lot of the people on this planet. And that makes it really, really hard. Next slide. So what do we need to do to meet the low carbon targets, given that developing countries want to develop? Well, here again is one of these long time series plots, but what we have to do on the y-axis here is our CO2 emissions per year. We have to stop emitting from fossil fuel sources here and turn our economy around so that we're not using so much CO2, not using fossil fuels, using renewables. And we can switch to low carbon energy sources right away. And I think the developed countries need to lead on this with solar and wind and developing the battery technology. We also need to cut energy demand. We need to change our behavior to reach any of these low carbon targets. And we need to develop new technologies. There's quite a bit of CO2 emissions that we don't have substitutes for. Solar and wind aren't substitutes for them. But really importantly, that I think a lot of people don't understand, is because the developing countries are developing right now, and because the CO2 emissions are so difficult to substitute for some things, we have to develop carbon dioxide removal techniques. And I think that the recent IPCC reports have made this so abundantly clear. And the technologically easiest are the land-based natural methods that we're going to talk about today, and how good are they and how useful are they? But we're probably also going to need technological methods. But the really important thing to understand is that carbon dioxide removal is going to be necessary for any of our carbon targets. Thank you.
Hi, I'm Peter Woodbury. I have the next section of our short presentations here. Next slide, please. So today we're talking about carbon sequestration in agriculture, focusing mostly on soil carbon sequestration. But I want to flip the script for a moment and say, as many of you know, if you've been involved with agriculture, there are many reasons to add organic matter or carbon to soil. In fact, greenhouse gas mitigation may not be anywhere near the top of most people's lists for the reasons to do so. So we're talking about improving soil health or soil quality, reducing erosion, reducing compaction, improving the infiltration of the soil for water, improving drainage, and increasing water holding capacity. These are among many, many functions that can improve with improved soil health due to additions of organic matter. Another important thing is maintaining or increasing crop yields. And that's important, obviously, for many reasons, but in the climate change context, it's important because of leakage. So the idea being, if we can have increased sustainable intensification and increased crop production on the lands that we have through both yield increases and through intensification of cropping cycles. So having crops on the land more of the time, we reduce the pressure globally and regionally to cut down forests to have new cropland available. So that's the connection here between crop yield and production and greenhouse gas mitigation. And then of course, we're here today to talk about sequestering carbon. And we're gonna talk about how that's temporary, that if you can add carbon to the soil, it can also be lost again. And as we just heard, we have a very long-term problem in climate change, so we need long-term solutions. If we're putting carbon in the soil, we need it to stay there. Next slide, please. This is just an example of another way to think about this leakage idea. And this is showing that as grass yield increases, the greenhouse gas emissions per unit of yield, per ton of grass production decreases. This wouldn't be a decrease on the area of cropland. So any greenhouse gas benefit of this would have to be this idea of avoiding leakage. Next slide, please. So one topic that's discussed frequently in terms of agricultural soil carbon is reducing tillage. And this is indeed possible to reduce or eliminate tillage in many systems. The issue is that the soil carbon that's added can easily be lost again if tillage increases. Next slide. There's also a lot of discussion of cover cropping in the US and some other places, but I'd like to focus instead on double cropping. So again, this is the idea of sustainable intensification by increasing the number of crops in a cropping cycle. So in New York State, that might mean adding a double crop over the winter to what's normally a single crop system. And again, we get these same benefits of adding organic matter to soil. We also might be able to scavenge and reduce some nutrient loss. And again, we can increase soil carbon. Next slide, please. So much as I love soil, I also love trees. And I want to mention them because storing soil carbon is not only temporary, it's also hard to measure and verify. So if we want to know whether a benefit's occurring, it's quite challenging. Trees are easier to see. They can be visually assessed, and you can assess the amount of carbon with a limited number of measurements of the trees and calculating the amount of carbon sequestration. So another possibility for carbon sequestration in agriculture, in addition to soils, is adding trees, one way or another, to agricultural systems. This is an example in New York State of a silvopasture. So it's grazing livestock, but also growing fence posts to keep the livestock contained, and growing black walnuts as a longer term crop. So it's a cropping system that has livestock, tree production, grazing, and also is sequestering carbon in the trees. There are many other ways to add trees to agricultural landscapes, and many of these have multiple benefits in addition to carbon sequestration. Next slide, please. So this is my final slide for my section, and this is from a paper on natural climate solutions globally, and it's just a selection of some of the pathways from this publication. You're going to hear more about biochar today. Conservation agriculture is what is, roughly speaking, also regenerative agriculture. So these would be practices such as as cover cropping and reduced tillage. And there are two bars here, one for peatland restoration and one for avoided peatland impacts. And of course, this is for the very high carbon soils that have the potential to lose a great deal of carbon on an area basis. So they deserve special attention. And trees and cropland, this was just a limited choice of growing alleys of trees among crop fields. So there's additional opportunities that are not shown here. The largest bars are avoided forest conversion and reforestation. And why am I showing those when our topic is agriculture? The reason is because the only way that these can be implemented is by increasing agricultural production on current agricultural lands. So this is taking low quality land out of grazing, a small fraction, about 4% globally, and replanting it in trees. That's the reforestation. That requires that we produce the livestock more efficiently on a smaller amount of land. So agriculture, improved production is the way that we can achieve both of these forest pathways. Thanks very much.
Okay, thank you, Peter. I'm also going to talk a little bit about soil carbon sequestration. So Peter's mentioned that there are many reasons apart from climate change why we might want to do it. It provides a lot of benefits, but I'm going to focus on, in this little talk, about its climate impacts. And I think Natalie set it up nicely with the point about the fact that we really need to think in terms of long-term temperature changes depend on your overall carbon budget. So it's the net amount of CO2 emitted or removed from the atmosphere that will determine your long-term temperature rise. So with that in mind, how much can we actually store in soils? I mean, it's hard to sort of open a newspaper or anything these days without seeing someone talking about how massive the potential is. Here's one modeling study. I could have used others. I use this one because it's a recent study myself, Johannes and some other collaborators have just produced, which will be available on our website soon. So we took the IPCC model and ran it globally to see if we, on cropland, for example, on every piece of cropland in the world, if we did all we could do in terms of increasing organic matter inputs and in terms of reducing soil disturbance, so no-till, that kind of thing. On grasslands, if we managed all of our grasslands so that we brought them up to native grassland quality with a lot of carbon stored in them. So there's a lot of degraded grasslands where that could be reversed. The third panel that we're called rewilding is what would, just as a thought exercise in a sense, to see what is the ultimate potential if we removed all humans from the planet and allowed all of our agricultural lands to go back to their native natural condition. How much carbon would that store? And on the bottom side, I probably don't want to spend too much time concentrating on it, just to be aware that, of course, it can go the other direction. If we continue to degrade our agricultural lands as we have been, we could lose up to over 100 petagrams of carbon. That's more. Now, a petagram of carbon, same as 1 billion tons. I mean, these sound like massive numbers and they're driving a lot of interest. Particularly, these are the projections to 30 centimeters. If you look at the whole soil depth down to 2 meters, it could be maybe 3 times that. But these give you a sense of just what scale we could do in terms of drawing down carbon. Is that a lot, though? Well, we have to reflect on just how large the climate change problem is that we're dealing. We really have an emissions problem that we need to tackle. At the moment, its average emissions over the last decade have been close to 11 petagrams of carbon as CO2 per year. So if we stored as much carbon as we could in the world's croplands, that would avoid roughly 16 months of current emissions. And that's only CO2, that's not even our other greenhouse gas emissions. Or in grasslands, 14 months of CO2. Removing all humans from the planet is maybe three and a third years. If we talk about the full depth of the profile, maybe a decade of emissions that we could be stored. And I think these numbers are quite, they give us pause to actually reflect on the fact that we need to focus on emissions with the most urgency, because any delay in reducing emissions can quickly, within a matter of months, outdo anything that we could achieve over a century in terms of ambitious programs of soil carbon sequestration in agriculture. So reducing emissions is the absolute imperative, and this is, if you like, icing on the cake. As Natalie mentioned, we need drawdown. We aren't going to get to a stable habitable climate without also removing emissions, but we really need to be cognizant of just what soil carbon sequestration can achieve in that regard. So I'd also like to make the point that soil carbon sinks are actually quite a risky place of putting carbon. Peter mentioned this as well. Anything that you put into the soils, if you return to business as usual practices, can be lost again. And in fact, it's not simply that there's a risk of return to business as usual, but the more soil organic carbon you put in the soils, if you put it there as soil organic matter, that soil organic matter also contains other nutrients, notably phosphorus and nitrogen, but others as well, which historically farmers have accessed these nutrients by tilling their soil organic matter and turning it into plant food. And the more you build up again, in fact, the more you increase the incentives to actually reverse some of these gains that you had. So it's not only risky because we might stop, but it's risky because people may actually want to stop. It's also risky because it's these incentives to reverse could actually play out in a farmer's favour if they decided to reverse any gains and they get paid again to sequester carbon to the same land. Also, it's risky in the sense that there will be huge incentives to do things like moving carbon from one place to another. So, for example, if you're getting paid carbon credits for storing carbon, you only put into that carbon scheme the land that is storing it, but you build soil carbon in that place by moving your crop residues, your manures and something else from other places. You get paid to store carbon that you've actually just relocated and you haven't actually put anything new into the system. And just the third thing I'd like to highlight in terms of things we need to be careful about with soil organic carbon as a sink is that it's really just not a very efficient way of using biomass. So in terms of, if you add a ton of carbon in the form of biomass into your soils, after 100 years, around 1% of that might be left. It depends, depending on your climate and the quality of the biomass itself, how low, the exact percentage, but it's a very small fraction of that carbon will remain. Most of it will be respired by microbes over the course of that century and even more into the future. Whereas if we took the same biomass converted to biochar, about 40% of that carbon would remain after 100 years in the biochar, plus we can get other benefits from things like avoiding nitrous oxide emissions from soils and co-producing energy with at the same time to offset fossil fuels. If we only burn that biomass to make bioenergy, we could offset a lot of fossil fuels. We don't get any carbon storage, but the climate mitigation potential is still very much larger than adding that biomass to soils. And it's expensive to do, but in terms of the most efficient way we know of really to use that biomass at the moment is if we both store most of that carbon by pumping it underground in the form of CO2 and release energy while converting it to CO2, which can offset fossil fuels, we can get a very much more efficient use of that same biomass. So it's economists often think in terms of something they call an opportunity cost. So if we want to say that building soil organic carbon is a net gain for the climate, that really depends on what we see as being the alternative, the best alternative. And if the best alternative for just squandering that carbon rather than that solar carbon, yes, of course it's a gain. But if we look at it relative to the other ways you might use that carbon more efficiently, in fact, it's a detriment, it's a loss to a climate mitigation because you've squandered away the opportunity to do very much more with that same carbon. Finally, just one last slide. I want to finish on a more positive note, is that soil carbon is not just soil organic carbon. So biochar, obviously very much more stable, although it's expensive to make. So we need a carbon price to actually drive that. But because it's much more stable, we can build up stocks very much more quickly, and we know that they will be there for very much longer. And another on the right-hand side, enhanced weathering. So if we're looking at the inorganic carbon cycle, adding basic rocks ground up to agricultural soils, they react with carbon dioxide dissolved in groundwater in the weathering reaction to produce carbonates and bicarbonates, which then store the carbon in inorganic form. And there is a very large global potential to do those, storing that carbon safely away long term and combating ocean acidification at the same time. Thank you. I'll pass over to Johannes now.
Thank you, Dominic. Thanks for organizing, Andy and Natalie, for steering us into this and setting us up. I would like to give you some messages first. Dominic, if you give me the next slide. Just some random, maybe seemingly random sound bites that I want to close this first round robin. One is that there's a big difference between the actual removal, so the carbon that's sequestered, and greenhouse gas emission reductions, and there might be trade-offs, and I'll show you some slides about that. And of course, there's food production also, as Peter so correctly mentioned, and that might be what the farmer is all after, whereas maybe society and policy making is after the others as well. And there might be trade-offs equally, but also some synergies, but not always synergies. There's really a large controversy around achievable targets, and you might have heard about the 4 per mil initiative. It's really important, and that starts to be more of the vernacular on the street, so to speak, that these goals are being more aspirational and inspirational than actually goals that can be achieved at any place, and the focus shifting more from the actual carbon accrual to soil health benefits. When looking at the organic carbon, it's really not about locked away, but the persistence is a result of functional complexity that is needed and that needs constant care rather than a one-time sequestration. There's spatial questions that are still ignored, and I'll show you something. And Dominic just mentioned inorganic carbon sequestration, and I show you no slides about that because there is not very much to be shown about it, but that we really need to figure this out as well and fold it into this discussion. So now here's why I tell you this. The next slide. So the 4 per mil Paris Accord was really a political move and has made a world of difference. You might be very, very critical, and you should be. And there was a storm of publication flurry at some point that has died down, luckily a little bit. But it was a world of difference for somebody like me who went to the UN conventions and political meetings for now 15 years or so. Or if you talked about soil carbon in the 2000s, everybody would laugh you out of the room. And now soil carbon, even Natalie talks about soil organic carbon, right? So even atmospheric scientists are talking about soil organic carbon now, which is really a massive change from 10, 15 years ago. The 4 per mil is really just a calculation of thinking through what is the net emissions between what we have in emissions from fossil fuel emissions versus the uptake in oceans and land, and the missing one to balance the budget at the time was about equating to 4 per mil of soil carbon stock. So that's really all. There was no further thinking. But I think there's it started accelerating a discussion that puts more fine points on what's actually achievable. The next slide. The concept of why do we have organic carbon in soil has fundamentally changed, and what it looks like has fundamentally changed over the last decade or so, from recalcitrance at that point of so-called humic substances and humus to a much more nuanced understanding of decomposition and mineralization phenomena in the soil, the importance of mineral stabilization and aggregate stabilization of organic carbon, and more the importance of what's called functional complexity, of the pore structures, the temporal dynamics, and the diversity of organic matter in soil, which all relates and says that we need to think about this as an ecosystem, the soil, and to achieve greater persistence, we really need to manage that entire ecosystem, and that doesn't mean we can put something in and forget about it. It's really that constant care versus one-time sequestration. That's how we need to think about soil carbon. Thinking about soil carbon and the dichotomy or synergy of greenhouse gas emission reductions and soil carbon accrual and actual CDR, carbon dioxide removal from the atmosphere, here illustrated with biochar systems that have multiple moving parts, as you can see. Introducing pyrolysis and biochar into an agro-ecosystem means that we can offset fossil fuels due to biomass fuels that reduces fossil fuel emissions. The transformation of an easily decomposable material into something that's biochar will reduce emissions of that material, but then also the biochar can have effects on carbon that's already in the soil, other greenhouse gases, methane and nitrous oxide, and of course increase or change, sometimes decrease crop production and lead to additional or less photosynthesis. So you already see the story between CDR and GHG emission reductions is not a straightforward one, but there are systems such as biochar and the others as well, where all of those play a role and are potentially synergistic if we're increasing soil health and increasing photosynthesis, or antagonistic, as I will show in the next slides. So we can look at, in the next slide, the relationship between systems greenhouse gas emission reductions here on the x-axis versus actual soil carbon accrual, CDR, on the y-axis, and plot some of the major and divergent or very different strategies. Cropland management is really a system where we manage inherent carbon, such as through less tillage or growing more diverse crops and crop residue management and so on. But you're dealing with carbon that's already in the system. Whereas biochar is potentially a lateral, and most often a lateral transfer of carbon and input, and behaves therefore very different. Whereas restored wetland is a system where you're reducing the output more than increasing the input. And you see that the relationship between system greenhouse gas emissions reductions and soil carbon accrual look very different. Whereas biochar has tilts more towards a greater greenhouse gas emission reduction at about the same carbon accrual. Restored wetland is sort of on the other side. That also is an interesting way to look at it. On the next slide, if you plot the soil carbon accrual, so more carbon sequestration in soils, against food production. And there you see very clearly, in most restored wetlands, we would assume that we're displacing wetlands with agriculture, if it happened at all, and therefore we typically see a reduction in food production and a negative relationship. Whereas with cropland management, we probably would always, or very often assume that we have more yield with more carbon in soil, although it plateaus at some point, but that there might be a negative relationship between those two as well. Whereas in biochar, with adding carbon, we're probably, in most cases, increase, though probably not linearly, probably asymptotic, increase yields and food production. Whereas with fertilizer, we probably increase food production, but in many cases not accrue more carbon, though there's interesting debates about that. To close, I want to make the point about the spatial redistribution of resources and carbon and nutrients, and that hasn't been done really at all. We sort of recognize that this is a landscape issue, that carbon is moving around the landscape and can be allocated in different areas, especially if we're talking about waste biomass, especially if we're talking about nutrient-rich Here an example from poultry litter and the conversion with thermochemical techniques. The example of the state of Georgia in the US, where the phosphorus resources with poultry are very differently distributed in the state than the phosphorus demands and therefore the biochar needs. And you can find different optima between emission reductions, profit, and greenhouse and total carbon dioxide sequestration. So you would plan your conversions and your collection stations across the state very, very differently if you would prioritize profit versus greenhouse gas emission reductions versus carbon sequestration. So those analyses have done only been incipiently, and they certainly lead both to opportunities for trade-offs and for some synergies. But that's really at the start of it only. So that was it from me. Thank you very much.
Thank you so much, Johannes and Peter, Dominic, and Natalie. We're going to pivot now to asking a couple of questions from my side to the panel. We'll kind of try to keep that short so that we at least have 5 to 10 minutes for the audience to chime in. But to the panel, I'd like to ask you first, what you think are some potential game changers in land use-based strategies for GHG mitigation that could be prioritized by the donor communities, private companies, and also younger scientists. What's your perspectives on that?
Well, this is Peter. Yeah, go ahead. Go ahead, Dominic.
Okay, I mean, I think we've mentioned a couple of potential game changers already in the talk, so I won't go on again about inorganic carbon and things like that, but a couple of things that we could add really are, one is recognizing that the greenhouse gas emission profile from agriculture is more about nitrous oxide than it is about the carbon story, and the potentials there are massive. Now, most of that is focusing on the fact that about 45% of nitrogen that we add to fields end up in a harvested crop, and maybe we can incrementally improve that nitrogen use efficiency. But the real game changer in that system, I think, is actually looking at the food system as a whole, where less than 10%, probably about 7 or 8% of nitrogen that we add to fields actually ends up in food that is consumed. So there are massive opportunities there to improve the system-wide efficiencies in the food system about getting nutrient recycling, avoiding emissions as nutrients are added to soil, and avoiding emissions from producing them. And the second game changer, I think, is going to be coming from freeing up land through new technologies that are coming now with novel foods that decouple food production from land. So, for example, renewable energies to feed electrons to microbes to grow protein, or artificial meats, and these kind of things. Just if we can free up land from food production, then we can do a hell of a lot more with it.
I'd like to chime in and thank you for bringing in the food system, Dominic. I think when people talk about greenhouse gas emissions from food waste, they almost only ever think about landfills. And thinking about if something like 30% of food is wasted in the US and similarly in many parts of the world, that's a huge opportunity for increased efficiency. So I think thinking about trying to not just find beneficial uses for some of those waste streams, but actually eliminate the waste streams entirely and increase that efficiency, as Dominic said, of nitrogen application to protein into the actual human diet is important. And I would also point to that overall topic as an example where we do need systems thinking, right? So there are gadgets and widgets and technologies that need to be improved, but I think there is huge opportunity to improve the way we manage systems such as the food system.
Excellent. Thank you, Dominic, Peter. Natalie, Johannes, anything to add, or we move on to the next one? Maybe I'll keep it going. Flip side of that, where do you think that we've already done enough research on GHGs in agriculture? What should we treat as settled issues so that we can focus on the bigger picture and some of the emerging game changers that you've identified?
Well, maybe I'll try something here. I do think that we that we're starting to converge that soil carbon sequestration is a possibility and that it has a high potential. Whether it can be achieved is a completely different story, and what can be achieved and where the trade-offs are. And I think I don't know who mentioned it. I'm sure it's on Dominic's mind, the trade-offs between N2O emissions and carbon sequestration. But Peter also mentioned the trade-offs between nitrogen sequestration and phosphorus sequestration and carbon sequestration. Those are all important considerations. I do think we're slowly past sort of questioning the whole idea and getting into the weeds of actually making it happen. And I think that's a really important step that will then show some of the weak parts of actually doing it, monitoring it, verifying it, and monetizing it, which will probably need to happen. There are countries that are actually doing it. There's always a sort of lingering vernacular that we can never measure soil carbon. That's impossible. And while I agree that probably modeling and practice-based assessments of soil carbon changes is the more practical approach, there are jurisdictions where they're actually measuring soil carbon after the fact and doling out money. So also that can happen. And we have not even really started developing the tools in the sort of digital agriculture space that we could deploy to make this less a soil sampling and dry combustion analysis approach, but a much smarter approach. So I think we're already down that road. I think we don't need to question the fundamental issues here. It's really about getting it done and developing the technology and the market mechanisms around it.
Thanks a lot, Johannes. Let me just ask one more question, and then we'll turn it over to the audience. You mentioned market mechanisms, and maybe that underpins all of this, that if we don't have a carbon tax or a nationally based cap and trade, maybe we don't have the appropriate incentives in place. But disregarding that, from a public policy perspective and from a private sector perspective, our current US and global priorities directionally correct with respect to the real opportunities for mitigating GHGs in agriculture? Do we have it right, and it's all about implementation at this point? Or what do we need to tell our friends in the political sphere in terms of what should be priorities?
Okay, I mean, I'll try chiming in here. It's a very difficult question to answer well, because there are so many different priorities from different policymakers and different policies around the world. So giving a generic answer to that is extremely difficult. But I think that at the moment, there seems to be more prioritization of these simple incremental changes, and really no one taking a real stab at the systemic changes to the food system where the big gains are to be had. So if I had a chance to say, so the short answer is no, I don't think that the prioritization is currently right, because they're looking at incremental improvements, small reductions in net greenhouse gas balances from agriculture. And we know that with really large systemic changes to how food is made and also to what people eat, dietary change can be a massive influence. And tackling some of these bigger, harder to tackle issues are actually where the big gains are to be had. And those are largely missing from the conversation.
Thanks a lot, Dominic. In the interest of time, I'm going to turn it over to the floor now. If you have a question, just unmute and ask. Or David, I think you had a question that you're writing to me privately. You want to pose that publicly? I think it's a very interesting one.
Okay, I was getting confused finally with what Johannes said at the very end, because when I listened to the other talks before, it seemed to me that the conclusion would be that the whole idea of agriculture, that storing soil organic matter in agriculture is kind of a very tiny part of the problem and probably fairly impossible, and it could easily be undone, et cetera, et cetera. So, you know, you said at the very end, though, Johannes, you said, oh, we know what we can do, let's get going. But I got from the earlier talks that the money would just cause distortions and the farmers would game it, and it's not that much anyway, and they're much, much bigger the opportunities. And my impression is we should just forget this whole thing and go back to the soil health idea, which is fine. I mean, what Peter started with, explaining all the benefits of how we can manage organic matter and do good things in yield and soils are fine. But to say we're part of the problem, part of the solution to GHG, maybe I missed the talk. So maybe I misunderstood you, Johannes. So I was all following along the first one.
David, rule number one, just listen to me. And then you're all good.
Okay.
No, I'm joking. No, this is part of the nuanced discussion, and I really appreciate it, because probably that's the impression that most people. I probably should let Dominic and Peter talk, but no, these are all nuances around it. But I'm putting words in their mouths now that they would probably not say we shouldn't do carbon. We shouldn't put carbon into the soil. And we shouldn't use the climate mechanism to help that. Whether the market mechanisms can be developed, I mean, that's always the question, especially in this country. But there are other countries who have already done it and shown that it works. So that's just a US problem. I would say I have not seen anything in Peter's and Dominic's talk that I wouldn't agree with. And yet I still agree with my points as well. So we have to get those together into one. Yes, it's a distributed issue. Yes, there are trade-offs. Yes, we probably always need to prioritize soil health. And that's the farmer will always prioritize that. And that's even now, if we drive down soil health with carbon sequestration, that not only the farmers is not happy about it and will not do it, but also in terms of many other systems such as biochar, it's probably better to make energy from biomass than biochar if yields go down, because then it's a wash in terms of the greenhouse gas balance. I haven't seen anything that is wrong in the statements that were made, and we need to get those all together in the mix.
Well,
I'll chime in on this for just a moment. I think we do have areas of agreement, and to some extent, I think Dominic played a very useful role of being a skeptic, and that's important because there is so much hot air around this topic, so to speak. I think in my mind, one of the challenges is there are technical solutions, and we can say, if you do this practice in this cropping system, you will increase soil carbon, and on average, you will increase yields, et cetera. So there are plenty of technical improvements to current management that take a systems approach to an agronomic system and say, look, we get better yields, we get better soil health, and we get reduced greenhouse gas emissions. So we need to promote those systems and make them happen. I think a big question in my mind is, how do you make that happen? And the simple idea in the US and elsewhere of a payment to an individual farmer for an individual practice on an individual field, whether that's in the US or in Bangladesh, there are huge problems with this concept. This is a tragedy of the commons, and I think the challenge is managing the land at a bigger scale than a single field or a portion of a field, et cetera. So some of the issues in measuring soil carbon or measuring benefits, if we could really get farmers in the Mississippi River Basin to change their fertilizer practices and change soil health practices at a massive scale, it wouldn't be so hard to measure it. right? If we weren't trying to measure it on every field.
Mm.
We could be doing this from tall towers and say there's less CO2 emission, there's less nitrous oxide, right? So I think in my mind, that's what we need to be thinking about is what are the social and political and organizational mechanisms by which we motivate change. If we can do that at scale, then some of these measurement issues go away and some of the gaming issues, et cetera, go away.
Thanks, Peter. Very interesting.
Okay. Can I chime in on this one as well? So thank you, David, for bringing that up. I was hoping to stir up a little bit of controversy and a discussion around this point. So mission accomplished. Yeah, I don't think we're in disagreement. I say I don't think anything in my talk said that doing soil carbon is a bad thing. It has many benefits for water quality, for cropping practices. You know, cover crops are useful in terms of farmers are doing them anyway because they're good in their cropping practices, not because they're trying to fight climate change. No-till is extremely common in dry lands because farmers want to do it because it helps them balance their water budget and improve yields. So there are many reasons for doing things that store carbon in soils. What I'm trying to inject some real caution about, though, is having people overselling the idea that it is a silver bullet, which is a lot of excitement around in the press, maybe not in academia as much, but if you look outside in blogs and papers and things like that, people see soil carbon as being the answer. That, you know, and that maybe gives people the thought that they're going to maybe take the foot off the pedal. We've got climate change sorted. We don't need to worry so much about the other things. And really, it can make at best an incremental impact. Although when we see, if we see numbers saying it stores a lot of carbon, of course, in the first few years when you start a practice, it stores a lot of carbon, but that doesn't persist. It reaches a new equilibrium, and you need to keep doing that practice forever. And after a decade or a couple of decades, you're not getting any impact on climate change. So this is why we need to be thinking about the long-term total potential rather than the short-term annual potential. And this is where I think we need to manage people's expectations, not because soil carbon is a bad thing, but simply because we need to maintain the sense of urgency about the other things to do with climate change, which are more impactful and more important in the climate change realm.
Well, that's why the 4 per mil was so intellectually dishonest, because they said that every year you could keep increasing at 4 per mil and keep on going and going and going and going. And maybe I just don't like intellectual dishonesty. Of course, they've pivoted quite a bit from that. If you go to their website, it's all about soil health, which is fine, and about yields, which is fine. But anyway, Dominic, you provoked me, so there you go. I've got to go to another meeting now. Sorry.
Thank you, David. We're over time, but I'd like to entertain one more question if Jenny is still online.
Hi, this is a question for Dominic and Johannes. So in Dominic, you had that blue and orange bar chart, and you show that basically biomass turned into biochar is basically equivalent in terms of its mitigation as bioenergy displacing fossil fuels. And so my question is, in helping someone and in the context of Natalie talking about how important it is to keep fossilized carbon fossilized, how do we give the relative value of, say, the 100-year biochar sequestration versus the 1 million year bioenergy displacement? So when we're helping people come up with a decision tree, now, of course, this is a yes and question because there are situations where you know, it's probably more amenable to making biochar versus bioenergy. So I'm just trying to understand, how can I think about how to frame it to a plus bioenergy, and when might you choose bioenergy, even if it has a slightly less total mitigation because it's keeping that fossilized carbon with a 1,000-year lifespan in the ground?
Yeah, so I had a paper a couple of years ago, 2016, I think, published in Nature Communications. Johannes was also a co-author on that, looking at exactly this question. When might we do? So I compared, in fact, bioenergy, biochar, and BECCS in the same thing. And it's a very complicated decision space because there are so many factors that might drive you one way or the other. If you're looking at places where there's very little opportunity to offset fossil fuels, for example, a country that has already got, or in the future already has a lot of renewable energy, for example, then that's going to push you towards favouring something that stores carbon rather than offsets energy. So the whole space that it operates in is quite complicated, but to distill a simple message from it, what it seemed to be is that in our current world, where our energy systems are quite carbon intensive and carbon prices are very low, we would probably prefer to make, most people would prefer to go more the bioenergy route at the moment. Now there's a transition once carbon prices go above about $100 per ton of CO2, sort of $300 to $400 per ton of carbon. And at that point, in locations where the biochar is actually really helping improve your crop productivity, because that's another of your dimensions, how does it impact your soil fertility? So in places where it's actually got a useful benefit, particularly in the tropics, to soils, there we would introduce more biochar. And then there's another transition. Some people sometimes think that if you want to store more carbon, if you want to improve the prospects for a technology, you just need to throw more money at it. And that's actually not true at all. If you increase the carbon price much beyond that, other things that were uneconomic at those carbon prices become the favoured option, like bioenergy for carbon capture and storage. So at very high carbon prices, in fact, you would even stop making biochar and direct all your efforts into these the tallest bar on that chart.
Yeah, no, I agree with that. And just one addition to that, one can also look at that sort of from a geopolitical and dimension, a very, very high perspective, and say, no, there are many ways to generate energy. But there's practically only one viable way to make organic carbon out of CO2. That's photosynthesis. So as much as we can, keeping CO2 in an organic form and creating value on Earth for humanity is a better way to do than returning it as CO2, even if we offset some other non-desirable thing. So that's sort of my more philosophical geopolitical view on that, why I would, if possible, always favor keeping more organic carbon on Earth.
Thank you.
Thanks, Dominic, Johannes. Peter, you also want to make a comment about N in methane.
Yes, very briefly, I just want to say, because the popular press focuses so much on carbon, it's really important to remember that in agriculture, greenhouse gas emissions are entirely dominated by nitrous oxide and methane, and that's totally different from any other sector. So at the global scale, those are a small part of the issue, but if you're interested in agriculture and greenhouse gas mitigation in agriculture, you absolutely have to pay attention to methane and nitrous oxide. And that's important because everything's not always a win-win. And of course, carbon and nitrogen are stoichiometrically linked in soil and elsewhere. So, you know, we're talking about carbon and nitrogen cycling. And that's important, I think, to remember, and in terms of focusing on solutions and avoiding problems disguised as solutions.
Excellent, thank you, Peter. We are 10 minutes over time now, so I think we should officially close, but I'd really like to thank the panel. It was a fascinating discussion, and I'm hoping you'll consent to do a spring follow-on, because I suspect that we could talk about this for a full day and only start to scratch the surface. So thank you so much, everybody. It's been a delight to have you put the panel together. And thanks everybody else for attending. See you next week.
This has been a production of Cornell University, on the web at cornell.edu.